So we're going to look at differential equation problems, and there is some pre-knowledge that is good to know, and that is this continuous growth rate formula. And the continuous growth rate formula looks like this. It's the end amount is equal to the start base e to the power RT, where R represents the continuous growth rate percentage. Or in some cases, it will represent the continuous decay percentage. This is an exponential growth formula or growth or decay formula, and many of the problems that we're going to do are going to end up in this form. So if we kind of know what the end result or our answer should look like, it'll give us an idea if we've done the differential equation properly or not. So for differential equations, the only type we can do right now are the ones that are separable algebraically by times or divide. So it needs to be in the form where we can put the dx with the g of x and our dy with our y expressions, and we can only do this if they can be separated by times or divide. Okay, so it needs to be in that form. It could either be g of x times hy, or in this case I've written it as division. Differential equations are functions that are described as a change, or basically the derivative. Now, some of these functions, and many of them in fact, have the changes described with the original function embedded in, or implicit function. Or in other words, the change is described in terms of itself. Okay, so this is these differential equations are often found in science, and these are problems that we often deal with in sciences. So for example, a chemical reaction, the change in the concentration of CH4, which is methane, is proportional to the concentration of CH4. So what that means is the change, or the speed at which the concentration changes, or how fast it's consumed, is dependent on how much methane is available. So the more methane is available, the faster it is consumed. Whereas if you only have a little bit of methane, the rate of change, or the amount of methane that's being consumed per second, is going to be smaller. And the differential equation looks like this. The change in CH4, concentration CH4 over dt, is equal to negative 0.2 times the amount of CH4 that's present. Okay, so that negative means it is actually a decay. So I'm going to rewrite this in terms of let the CH4, concentration of CH4 be y, so it's a little bit more familiar to us. So dy over dt is equal to negative 0.2 times y. Okay, so this is our differential equation. We are able to separate this algebraically, so we're going to do that. So I'm going to go dy over y, and that's going to be equal to negative 0.2 times dt. So I've separated my dy and dt. I'm going to now integrate both sides, and I'm going to end up with log y is going to be equal to the integral of negative 0.2 is going to be negative 0.2 times t, and we can't forget the plus c. Okay, so we're going to have to solve for the plus c, and we have our initial condition. So the initial concentration of CH4 is 3 molar. So that gives us our time is 0, y is 3.0. And we can plug that in to solve for plus c. Now, I do want you guys to recognize that these problems are exponential decay problems. So it does end up fitting our continuous growth rate formula. And that plus c actually is going to end up being the same as our starting value. Okay, the start value, which we're going to later call k. So I'm not going to solve for the plus c in this form. I'm going to rewrite this as y equals e to the negative 0.2 t plus c. And again, instead of solving for the plus c here, I'm going to rewrite this as y equals e to the c times e to the negative 0.2 t. That plus c here is the same as e to the c. And in fact, I'm going to change that into y equals, I'm going to just call that something different. I'm now going to call that k, which is the starting value, e to the negative 0.2t. Now, I could solve for the plus c in it at any point, but I'm going to now solve for the plus c as a k. So plugging that in, 3.0 is equal to k e to the negative 0.2 times 0. Okay, so that becomes e to the 0, so which is 1. So we end up with k, our k value equaling 3.0. So now we have our equation. It's going to be y equals 3.0 e to the negative 0.2t. Okay, and again, notice that our end amount is our y, or our final concentration of CH4. And that's going to be equal to the starting amount, which is 3.0 molar, e to the negative 0.2t. And that negative 0.2 actually represents a 20% decay rate. Okay, so there's our differential equation. It is an equation. This differential equation happens to be a derivative that is described in terms of itself.